Hi, welcome. This is complex analysis, fifth session, holomorphic functions 5, and we are continuing with the Cauchy-Riemann equations. In the last session, we proved if a differential function, holomorphic function, is given, then it satisfies the real and imaginary part u and v satisfy the Cauchy-Riemann equation. Therefore, we said it's a necessary condition; it may not be sufficient. Okay. So today we want to put an extra condition and to prove if a function f from c to c satisfies Cauchy-Riemann equation and also its partial derivatives ux, vx, ui, vy, they are all continuous, then the original function is holomorphic. The proof is, I do not know how, how well you understood. You might have seen it from functions from R2 to R. If you have a function f of xy from R2 to R, and if the partial derivative, if the function is differentiable, then the partial derivatives del f by del x, del f by del y exist. But if the partial derivatives exist, the function may not be differentiable. Sometimes, classically they will say total derivative may not exist. This thing you might have seen. A sufficient condition is if the partial derivatives are continuous, then the given function is differentiable and the total derivative exists. Don't worry, I am actually going to give that proof because that's very crucial, and you will see how easy it is. Once you understood, you see that you can do it at any time, and it also sets up the notation. Okay, let so, yeah. So let us recall. Okay, suppose f is a function from u in R2 to R, right? Then if f is differentiable at, let us say, xy, if there exists a linear map T from R2 to R, so that T of hk equal to AH plus BK for all hk in R2, and such that modulus of f of x plus h y plus k minus f of xy minus T of hk is less than epsilon times norm of hk. Okay, for every epsilon greater than 0 there exists a delta positive, so that 0 less than norm of hk less than delta implies this. This is the definition. In case you have not learned, okay, this is a nice place for you to learn this. And what is known is, if f is differentiable at xy, then the partial derivative del f by del x, del f by del y exists at the point xy, but the converse is not true. Okay, so what we want to do is the following. Okay, so we just want to put a lemma. This lemma actually will prove what you want anyway. So let me just do u be from R2 to R. This may be an open set. Okay, it's a function. Let us say omega an open set in R2 to R. Okay, so besides that, the partial derivatives ux, that is del u by del x, and uy, that is del u by del y, exists on omega. Then okay, for all hk in R2 such that xy plus hk lies in omega, we have f of x plus h, let me say u of x plus h, y plus k minus u of x y equal to ux at the point xy into h plus uy at the point xy into k plus h into some phi 1 and k into some phi 2, where phi 1 phi 2 go to 0 as hk go to 0. Right? Again, to make you understand, think of this as a mean value theorem. Okay, this is what it says. Right? So again, let's look at a one variable case. Suppose I have a function f from some interval j to r, okay, continuously differentiable. Right? Let's say at a. Then that is f dash a exists and f dash is continuous at a. Then for all x, so that fx and j, we have fx minus fa. We know this is some f dash of y into x minus a. But this I can write as f dash of x into this x minus a, yeah, f dash of a into x minus a plus right, f dash of y minus f dash of a. Do you follow that? F of x equal to f dash of y into this mean value theorem, right? But that is equal to some, add and subtract this, okay, f dash of a minus fa plus fa into x minus a. Alright, so this is, so you have f dash of a into x minus a. This is like your h. Suppose x equal to a plus h, this is your h into some phi 1, okay, of, okay, this depends upon your x and a times h, okay, just phi 1, some quantity which depends upon x, a, etc. times h. This is h, right? And what do I know? Because I assume f is continuously differentiable, therefore x tends to a. Remember, y lies between a and a plus h, or y has to be somewhere here, right? Therefore as x tends to a, I know that y also tends to a, right? Therefore f dash y will converge to f dash a by continuity of f dash at a. Therefore this goes to 0, phi 1, therefore phi 1 goes to 0 as x goes to a or h goes to 0. Do you understand this? This is all we need. The same logic is what we need. Therefore pause, review, proceed. See, now please understand, that's why real analysis is very important. Okay, you can see I keep on harping upon that fact, because many people do real analysis, think that they pass the exam so they don't need, but you will see every time, if you had understood real analysis well, it helps you to master analysis and deal with any kind of analysis in future. Okay, right, so let's go back. Now this is what you want to do. Yeah. So let us go to the proof of lemma. Okay. So let us look at f of x plus h y plus k minus f of xy. Right. What is the trick? The trick is very simple. Suppose my xy is here. I'm just writing although the h k are all positive, therefore everything like and xy is in the first quadrant, etc. But that need not be the case. Therefore, you can go up to x plus h here. Okay, this will be x plus h y, and then do this. Therefore, you see that. So here, if I restrict my f to this, okay, that's going to be a function of x alone because y is kept fixed. Whereas, therefore, this is a function of x. If when f restricted to this, whereas when I restrict f to this, it's a function of y, because y is the one which is going to vary. This is y plus k, right? So that is the trick. So we add and subtract. Okay, therefore f of x plus h y plus k minus f of, you come from here to here, this is going to be f of x plus h y, right, and plus f of x plus h y minus f of xy, right? So we are doing this first and then this is the second, right? Therefore what do I know? So I know that now x plus h same, therefore this is a function of y as I said. Therefore I have a partial derivatives with respect to x I will write as fx, fy, etc. Right, and my x dash will be a point between x and x plus h, y dash will be a point between y and y plus k, etc. Right, so this will be some fx into see this is sorry fy into x plus h some y dash, right? There is going to be a point where in between these two things, so the point is going to be somewhere here. Okay, y dash, right, into what is this? This is into k. Yeah, into k, and then this what this is fy into f of x plus hx. Therefore this is going to be x dash times y into h, right? But what did our theorem say? It's exactly in the first, in the one variable case, I would like to write it as fy into xy into k. Therefore this will be fy into x plus h y dash into k minus f of fy into xy times k. Therefore k comes out this. Do you understand? I am adding and subtracting fy x y at k, right? That's why I did the one variable case. You understood that well, the notation will not bother you. You know if the concepts well, then the notation is not intimidating. Many people are bogged down by notation, but if the concepts are clear, it never bothers you. And similarly the next one, what is the next one? That is this is fx into some xy times fx into x dash y minus fx into xy into h. Yeah, therefore this I can write as exactly, this is my phi 1, this is my phi 2, right? And by continuity of fx and fy, what do I know? Phi 1 goes to 0 and phi 2 goes to 0 as hk go to 0. Okay, so pause, review, proceed. So this is one thing you should learn. You see that once one variable, many teachers directly go to the proof, right? Whereas what we did is we said we don't need that. Yeah, understand the one variable case and show how we reduce the problem to one variable case, right? And therefore the notation does not bother us. Okay, so this is what you should learn. Whereas textbooks immediately, for example, this lemma also they will not prove. They will try to prove the same lemma will be part of the proof, and you can go back and see this actually shows, okay, the total derivative exists. The total derivative is, as I said, so if I take a equal to fx of xy and b equal to fy of xy, then we have proved f of x plus h y plus k minus f of xy minus ah minus bk, okay, there is less than or equal to some mod h into mod phi1 plus mod k into mod phi2, right? Therefore this divided by square root of h squared plus k squared, this will be divided by square root of h squared plus k squared, square root of h squared plus k squared. Okay, I am going through all these things because the same trick I am going to use. But then remember, mod h by square root of h squared plus k squared is less than or equal to 1. Therefore this is less than or equal to mod phi 1 plus mod phi 2, which goes to 0 as is hk go to 0. Therefore f is differentiable on u in R2. Okay, this is the proof you must have seen in two variable calculus. Okay, directly they will try to prove it, whereas what did I do? I tried to show the one variable what happens and use it to prove a similar thing for two variable, right? And then used it to show that if continuous partial derivative exists, the function is differentiable. Okay, do you want to thank me? Yeah. You might have gone through the proof, many of you may not have understood, or you thought that notation is so complicated. Now the concepts makes it clear. This is what you have to learn. Okay, right. Okay, this is what we are going to use. This last part we don't need it, but what all I need is a lemma. Okay, right. Now let f be a function from C to R C. Okay, assume that f equal to u plus iv and u and v satisfy Cauchy-Riemann equation, and ux, uy, vx, vy are continuous on u. Then f is holomorphic on u. That is the theorem we want to prove. I forgot to do the screen share. Okay, I do not know where I did. Okay, so go back. So you prove f is differentiable as a function of R2 to R with a equal to the partial derivative of fx at xy, b equal to partial derivative of y with f to partial derivative of f with respect to y at the point xy. Then this minus square root of h squared plus k squared should go to 0. This is the definition. But I have an estimate. The numerator is less than or equal to mod h into mod phi 1 plus mod k into mod phi 2 and divide by square root of h squared plus a squared. Then I observed mod h by square root of h squared k squared is less than or equal to 1, and similarly mod k by square root of h squared plus k squared. Therefore the first term is less than or equal to mod phi 1, the second term is less than or equal to mod phi 2. But what do I know about phi 1 and phi 2? They go to 0 as hk go to 0. Therefore we proved the result. Okay, so we had come, even though it's not needed for our complex analysis course, okay, I use the lemma to prove if continuous partial derivatives of a function from R2 to R exists, the function is differentiable and the total derivative exists. Okay, and typically in classrooms the teacher would have started with writing f of x plus h y plus k equal to blah 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 and got the proof. But what I did was I looked at the first R to R case, understood what is happening, then we mimic the same thing to get a similar lemma in R2, then the trivial estimate. That is why one kind of breaks any kind of difficult proof into small pieces, understand what is happening. Yeah, I hope this helps you. Okay, now come back. This is the main result of today's session. If I have a function from C to C, okay, and if it satisfies Cauchy-Riemann equations and the partial derivatives of the real and imaginary part are all continuous, that is ux, uy, vx, vy are continuous, then I want to prove if it's holomorphic on U. Okay, this is what we want to prove. Yeah, so if you want to prove, what should I do? Okay, first thing is you have to have you have to prove this. This is very okay. Instead of h, let me use xi as the increment. Okay, therefore I have to prove f of z plus xi minus f of z, okay, by xi. This goes to some limit, right? This is what I have to prove. So if I want to prove differentiable, okay, I have to somehow find what should be the derivative of dash xi. Okay, so somehow we have to guess what is f dash z. Then only we can try to estimate. Then we will try to estimate f of xi by xi minus f dash of z. Then I can show this goes to 0. Right? Now how do I find it? This is where our earlier knowledge helps. First thing is, what is the candidate for f dash xi? Remember, when I started with Cauchy-Riemann equation, I said f, yeah, del f, that is f of z plus xi by f of z, if assuming it's differentiable xi, okay, f dash of z, we said this is nothing other than fx, that is ux plus ivx. Okay, this is the first CR equation we derived, where I allowed xi to belong to R and xi go to 0 in R. Okay, using that we got this. Okay, recall this. This gives us a candidate. Okay, so my guess is f dash z is ux plus ivx. Right? So what should I do now? So what I want to do is, therefore f of z plus xi minus f of z minus, okay, this is ux plus ivx into xi, okay, this goes to 0, as xi goes to 0. Yeah, that is, we need to prove this. Right? Now what is the trick? If you had been following my analysis, now you know the trick. Here there is a u and there is a v, and whereas I have f here, therefore what should I write? F as u plus iv, etc. Right? Are you following me? Then I'll break f into u and v, therefore u plus iv, therefore it will be u at x plus, so let me write xi equal to h plus k, xi equal to h plus ik. Right? This is h and k are reals now. Right? Therefore this I can write as u of x plus h y plus k plus I times v of x plus h y plus k. Do you understand this? Similarly I will write this. Now what do you think I will do? I will break the real part u and collect all of them. U minus this one u right? Now what will I do? I will use the lemma to this minus this, I know what to do, and I will use the lemma to v of x plus h minus v of xy. Do you follow that? Times I. Have you understood? Okay. Then what will I do? Now remember, when I write here, this is all just thinking. Okay, don't go into the proof. Now when I write u of x plus h y plus k minus u of xy, then I know on the right side I have ux uy times something, right? And similarly v of x plus h y plus k minus v of xy, I will have vx something plus vy into something. Yeah, please go through that. If you want, let me just go through the lemma. Yeah, see, ux into h, vy into k, uy into k, right? Similarly for v also I will have, and h into this some thing. You follow? Now what do you think I should do? I want only ux plus I vx. So what do you think I will do? Wherever uy is there and vy is there, I will use Cauchy-Riemann equation to convert them and club them together. Is the idea clear? Yes? Yeah? Let us hope so. Okay? Right. So let us do that. So this is equal to this. So let us ignore all these things. Okay? So this is equal to, what do I know? Ux. Now if you allow me, I will not write, see, I have to write something, right? So I will not write, I will use the same thing, ux into h, yeah, plus uy into k plus phi 1 h and phi 2 k. Just make sure this is what we got in the lemma. Right? Ux, I'm just writing this. Where am I? Yeah. Ux into h, uy into k, h into phi 1, k into phi 2. Is it clear? That's what we are doing now. Yeah. And similarly, I'll have I vx into h plus vy into k, yeah, right, plus I times something, h into, let me call it xi1 and I into k into xi2. For v, I will, instead of phi, I will call it phi 1 and 2. So what do I know about phi 1, phi 2, xi1, xi2? They all go to 0 as hk go to 0, which is same as saying xi go to 0. Xi is the increment. Right? Now we know what we want. You want the ux plus I vx. Okay, let us do that. Can we do that? There is ux. Okay, then I vxh. Therefore, I can write ux plus I vx into h. Now remember this into xi. That must be my f dash z into xi, right? But xi is h plus ik. Therefore, I should be able to do this, and then I into ux k and I into I minus 1. Therefore, it is vx into k. So I have to correct those things. Are you following? Yeah. So let us do that. So now let us look at k. So I have ux into h. Yeah, right. Okay, let me just, so what are our Cauchy-Riemann equation? Ux equal to vy and uy equal to minus vx, right? So I want a ux, therefore what should I do? I should look for vy. Is it clear? Therefore I have I times vy, there is a k outside, let me do that, plus, then what do I have? I want uy, I want, this is vx I got, ux I got, therefore I have to get a vx, that means uy. So where is uy here? Yeah, uy is here, right? This one I can write as uy into k. Let me look at uy k. This I can write as minus 1 into I squared into uy into k. Therefore it's minus I squared into minus uy into k. Therefore it is I, there is an I, right? Therefore minus I uy into k. Yeah, but that is going to be plus all those things, phi 1 h plus phi 2 k plus I h1 xi 1 plus I k xi 2. Therefore this again is using Cauchy-Riemann equation. I is out, Vy is Ux, and minus Uy is Vx. Therefore Vx, there is an I outside, remember that, into K plus, right? So this is your thing. So this is Ux plus Ivx into H plus Ik plus this object, right? Therefore f of z plus xi minus f of z by xi is ux plus ivx, right? This equal to modulus is less than equal to mod h into mod phi 1 plus mod k into mod phi 1 2 plus mod h into mod xi 1 plus mod k into mod xi 2. Okay, yeah, that whole thing divided by 1 by mod xi, right? But as I said earlier, mod h by mod xi is less than equal to 1, etc. Right? Therefore this is less than equal to mod phi 1 plus mod phi 2 plus mod xi 1 plus mod xi 2. It goes to 0 as xi, which is h plus ik, goes to 0. Right? That's it. So proved the result. So did you follow the proof? Is it easy? Right? In spite of the notation being complicated, that's what you should observe. That is why I keep telling my students always, try to understand the concepts well, because the notations are symbols. They convey certain concepts, certain ideas. If the ideas and concepts are clear, notation will not intimidate us. You will not be afraid of them. You will not be confused because of them. Okay, even if there is a slight mistake in the notation, you will know what is meant. Okay, my standard example is, if I write something like 2 plus 3 equal to 6. Okay, there are two ways you can think. Okay, namely, Professor Kumaresan does not know mathematics. Yeah, or maybe 2 plus 3 he wanted to write 5, it's a typographical mistake, or he wanted to write 2 times 3 equal to 6. So plus is a mistake, it should be times in multiplication symbol star. Now again, if your concepts are clear, namely, before I wrote this, something went before that, right? That context will make sure whether I wanted to say 2 plus 3 or 2 times 3. If it is 2 plus 3, then writing 6 is a mistake, it should be 5. If the context made it clear it is star, then writing plus is a mistake, it should have been multiplication symbol times or star. You understand that? That is why understanding concepts are always very important. Okay, right. Now I have done the standard thing, but there is a very beautiful modern geometric way of looking at Cauchy-Riemann equations. In fact, we will get it much cheaper. I will say this, but you don't, that will be a separate video altogether completely. You can skip it, you don't have to understand, but I will explain what it is because I have still some time. So let me explain that idea. Suppose I have a function f from u in C to C, right? Now if I write f equal to u plus iv, right, the open set u I can think of it as a subset of R2 also. In the sense I have to identify, right? Z goes to Z in x plus iy goes to r dot per xy, right? Therefore, if you want, I can simply say ur. Okay, ur denotes real power. Okay, are you following? So ur is nothing other than x comma y, so that x plus iy is in u. That's it, right? This is an open set. So it is, we will think of as u also as an open set of R2. Now do you see I have a function capital F where from u in R2 to again R2. Now you give me xy. What will I do is I will write it as u of xy and v of xy. That is, this is intuitively x plus iy goes to f of x plus iy, which is u of xy plus I times v of xy. That goes to, I identify with r dot per uxy vxy, right? Yeah. Now this is the modern version. The thing is, f is holomorphic on u in C if and only if capital F is differentiable on u and its components, that is f equal to uv, its components u and v satisfy Cauchy-Riemann equation. This is the theorem we will prove in one of the videos, but this is strictly not needed in the standard course. But if you are interested in understanding the subtlety and the geometry, where the geometry is involved here, you will see that. The basic trick is, C I can think of as a two-dimensional real vector space. R2 is also a two-dimensional real vector space. There is an obvious correspondence. X plus iy going to x comma y is a real linear isomorphism, right? Then I can ask, when I give, okay, I will talk about it later, I don't want to. Now notice that the very interesting thing is, you simply said u and v satisfy Cauchy-Riemann equation, but you didn't say u and v, the partial derivatives are continuous. Now go back to the earlier one and see, again you might have seen here capital F, the components are u and v. Okay, assume that the partial derivatives ux, uy, vx, vy all exist and they are continuous, then you know capital F is continuously differentiable, and hence you will see f is also, right? So many analysts got little confused and they thought even this result is wrong when I first mentioned that. This is about almost 40 years ago. Yeah, little more than that. Okay, now it's in some of the books it may be available. It is available. But when I found it, when I was teaching a course in TAFR in 1980s, I found this. Right. As I said, it's not strictly needed. But if you are interested, you should wait for that video also. Okay, I hope you enjoyed and leave what I said the last few minutes. But to Cauchy-Riemann equation, you saw how I built up very easy. Yeah. Again, believe me, many of you approach mathematics in terms of exams. Don't. This tells you if you can understand the concepts well, you will have confidence in yourself. You can work out the details anytime. Maybe you require more time. Okay, that's it. Okay, we will meet again. All the best. Stay safe. Take care.